Can you hear me? Okay, perfect. Let's begin. Okay, so let's start this. Let's go here, and you can all see the screen, right? La, 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 la. This is visible, yes. Can the volume be increased? Of course it can. Is it better now? Okay, perfect. All right, excellent. Okay, so let's just begin. So we stopped the last class at binary, octal, and hexadecimal. I'll add a couple of more things from section 4.2 before I move on to section 4.3. So the first thing is, and this is going to be, all right, so the first thing is addition of binary integers. All right. Okay, and so let's see how we'd go about adding a couple of numbers in binary notation. So let's just recall what we usually do when we add two numbers, right? The usual process is as follows. So let's suppose if I want to add 234 to maybe 75, what we do in decimal representation is we add these two numbers, and the idea is that over here the answer is going to be in decimal representation as well. So each digit can be from 0 to 9, right? And so if the sum is 10 or greater than 10, then we move a carry to the next digit, right? So this is simply 9. So we don't need to carry because the result is less than 10 and we can represent it in these numbers. But for these two, the result is of course 10 and it doesn't include. So the way we'll do it is we'll see that if it's 10 or is it greater than 10. So I can just write it as 10, which means I will put a 0 here. I will take this last digit and put it here. And this I will carry to the other side, and then this becomes 1 plus 2, simply 3. And so that's how we'd do a addition. Okay, but that is in decimal. What we need to do is replicate this process in, let's suppose we were doing some binary integers. We had 1110 and we had 1011, and we wanted to add these two numbers. Now of course each, oops, what is this? No, let's undo that. Okay, and so the idea is that each digit over here, we have the possible digits over here will be from 0 to 1, right? And if it's greater than 1, if it's 2 or greater than 2, then we'll need to carry to the other side. And so we'll do 0 plus 1 is simply 1, so there's no carry. 1 plus 1 is 2, so of course we'll take it, we'll see whether if it's greater than 2, then we'll try to see how much bigger it is than 2. If it's simply 2, then of course we can just write it as, so 2 can simply be written as, in binary it's just written as 10, right? And so the last digit now is 0, which we place here, and we carry the next digit, which is 1, and we carry it here. Again we have 2, we place the last digit here, carry the 1. Now the next one is 3. So for 3, we know 3 can be represented as 1, 1 in binary, because this is 1 times 2 to the power 1 plus 1 times 2 to the power 0. So that's 2 plus 1, which is equals to 3. And so 3 can be written as 1, 1. So we place a 1 here, and the next one that is carried is placed again here. So 1110 plus 1011 is added and gives this result. And the idea is how to write an algorithm for this process. And here's a simple algorithm that we'll define in terms of. So notice something, that at each point we were doing something like this. What we were doing, if the numbers, if let's suppose a was the number a n minus 1, a n minus 2 up until a 0, and b was the number b n minus 1, b n minus 2 up until b 0. Notice that these are the digits of the numbers and of the number a, and these are the digits of the number b. And so the way we add this is we did a process something like this. We added these two numbers a naught and b naught, and we tried to see whether it was bigger than 2 or not. If it was bigger than 2, then we write it as follows. We write it as c naught times 2, where we capture the multiples of 2, plus s naught, which is the last digit of our result. So for example, in the first case, when we were adding 0 and 1, the c naught was 0 because it's not bigger than 2, and s naught was 1. So in our example over here, what we had was a naught was 0 plus 1, which was equals to 0 times 2 plus 1. And so c naught was 0 and s naught was 1. Okay. And in the next step, what we need to do is we need to add in a1 plus b1, and if there was any carry, then we add that carry to this addition, next addition. So when we add these two digits, we also need to check whether there was some carry or not. If there's no carry, then of course it's just 0, which it is in this case. But of course, if you write it as a general algorithm, then we'll need to make sure that you add c naught as well. And then again, you repeat the process where you write c1 times 2, where c1 is the next carry and s1 is the next digit of your result. And you keep doing this up until you get to the point an minus 1 plus an minus 2, plus bn minus 1 plus cn minus 2, and you write it as 2 times cn plus cn minus 1 plus sn minus 1. And lastly, your last digit sn will be this last carry that you have, so cn minus 1. And so the sum a plus b will have the digits sn minus 1 up until s0, and this would be your sum. Okay. Logic behind multiplying. Okay, let's answer these questions in sequence. First, Dania's question was, sir, can you please explain how we get to know that 2 is 1, 0 and 3 is 1, 1? Well, that's something that I used from memory, but you can try decimal to binary conversion for 2 and 3. So if you want to convert 2 and 3, you will need to convert decimal and binary, which we did in the last class. So check out the note for that and see. I remember how to do that, so it's actually pretty easy because the first digit represents 1, the second digit represents 2. So if you have 1, 0, then we know that this is basically 0 times 2 to the power 0, and this is 1 times 2 to the power 1, right? And so check out the previous class for that. And what's the logic behind multiplying c by 2? The logic here is that, for example, let's suppose you were adding 3 numbers over here in your decimal representation. In the decimal representation, let's suppose you were adding 3, 7, and, or rather 7, 5 and 9. Let's suppose these 3 numbers were being added. What you would do is, so this is 7 plus 5, which is 12, 12 plus 9 is 21. Now for 21, what you can do is as follows. You can write 21 as 2 times 10 plus 1 times 10 to the power 0. You're again checking the digits, right? And so the last digit will come here, and this will be carried out to the next one. Now the idea is that you're looking at multiples of 10 here, because you are in decimal representation. When you come to binary representation, you're looking for multiples of 2. So the carry will be a multiple of 2. So for example, when you add, let's suppose, when you add 3 digits together, 1, 1, let me do this somewhere on the side. So for example, if you add 3 digits, 1, 1, and 1, and if you were doing this addition, what you would do is you would check what the result is. The result of 1, 1, 1 is of course 3, which can be written as follows. 3 can be written as 2 times 1 plus 1. So you're looking for how many multiples of 2 you have, plus the last digit, which is 1. So the way we write this is it's 3 is equals to 2 times 1 plus 1. So 1 will be placed here, and how many multiples of 2 you had? You had 1 multiple of 2, so you will carry 1 in whatever the next sequence is, whatever the next sum is. But the idea is 2 is being multiplied because you are in binary representation. Okay. Okay, let me do it in some other way. Let's look at the same thing that we did, for example, over here. Let's follow this example. What we were doing essentially, when we were doing this addition, 0 plus 1, 0 plus 1 is equals to, you need to check how many multiples of 2 do you have, because that's the next thing that will be carried. For the reason is each digit in your binary expansion can hold up till 2, right? So it's either 0 or 1. If you have 2, then you have to move to the next digit. So you check how many multiples of 2 do you have in your sum. Over here, when the result is just 1, you don't have any multiples of 2, so you don't need to take anything as carry. You can just write it as, you need to check c times, how can you write this as c times 2 plus s? Do you have any multiples of 2 in this? You don't, you just have 1, so you write it as 1. But for example, in the last case, when you were doing 1 plus 1 plus 1, 1 plus 1 plus 1, now you have a multiple of 2. You can take this, both of these as just 2. So it's some multiple of 2 plus this remainder 1. So this is simply 1. And c, of course, over here is just 1 because this was 2. So 1 times 2 plus 1. And this will be your carry digit. Does that make sense now, Jafar? So maybe if we do this summation 1110 and 1011 in this process, let's just look at this. Let's repeat this summation 1110 in binary plus 1011 in binary. And so what we have is, so if this is A and this is B, what you have is, this is the first digit A0, A1, A2, A3. This is B0, B1, B2, B3. So let's suppose we have to do A0 plus B0. That's the first step of the procedure. You take A0 plus B0. And the way we do it is simply 0 plus 1. Do we have any multiples of 2? We don't. So the way we'll check how to write this in C0, 2 plus S0. Now, of course, there's no multiple of 2, so C0 is simply 0. So this is 2 times 0 plus 1. And so over here, S0 is your digit of the sum. So last digit of your sum is simply 1. And C0 is the next carry which you will add to the next 2 digits. So A1 was 1. So we need to do A1 plus B1 and take the carry from here and add it here. So the second digit is 1, the second digit over here is 1, so 1 plus the carry from before is just 0, so this is 2 now. And 2 can be written as, of course, this can be written as 1 times 2 plus 0, right? And so this is where the carry comes in. So the carry came in the next digit. This is the carry that came from adding these two numbers. And so notice that you can write this 2 as 1 times 2 plus 0. So this is C1 and this is S1. And so my next digit of the sum is 0. So I know that my number is 1 and 0. And for the next addition, I will do A2 plus B2 plus C1. And so A2 is 0, A2 is 1, B2 is 0, and C1 is 1. So we'll add 1 plus 0 plus 1. Again, we have 1 times 2 plus 0. So same procedure keeps on repeating. Okay? And so you can complete this procedure on your own. Just check what's the carry from the previous step and add it to the next digits that are being added. If there is still some confusion, I recommend that you try the procedure yourself and you will realize what's happening. If you still have any queries and you are unable to understand what's going on, let me know. But it would be clearer if you try to do it on your own. You just need to check how many multiples of 2 do you have in your sum. Okay? And so let's try to define this as an algorithm. And so we have algorithm for addition of integers. Addition of integers. And the way to do it is as follows. So the addition algorithm is simple. We define procedure. The procedure is that we want to add two numbers which are A and B. The first step is to set the carry as 0 and then start the loop for j from 0 to n minus 1. Notice that the number A is an minus 1, an minus 2 up until a0, and the number B has digits bn minus 1, bn minus 2, ... b0. Okay, so we start off from the first digit. We say we're going to add these two numbers. We're going to add aj plus bj plus c, and because we want to find the multiples of 2, because we want to find the digit, the way we'll do this is we will divide this number by 2 and we will floor it. The next thing that we do is we define Sj as follows. So this is, we were checking how many multiples, so D tells me how many multiples of 2 do I have in my sum. Then Sj is Aj plus Bj plus C, and we subtract these multiples of 2 from it, minus 2 times D, and then C we set to be D because that was the carry that we're going to do. And we keep doing this loop up until we get to the last digit. This might be a bit confusing, we'll go through this, but the idea is the same. And so the last digit Sn is simply C, the carry that's remaining in the last digit, and we return the digits Sn, Sn minus 1, Sn minus 2, ... S0. Okay. Alright, so let's see how this procedure works in practice. Let's put a box here. Okay. Oops. This is Okay, I still don't have the hang of this. Okay, there we go. Okay, and so that's the addition algorithm. All right, let's follow this addition algorithm. What it's saying. Let's try to do 1 0 1 1 again. So 1 1 1 0 and 1 0 1 1 using this procedure. And I'll just do the first step for you, and you can follow it on your own. So first we have j equals to 0. And so what we need to do is we need to find d to be the floor of aj. So a is 0 plus b 0 plus c. C we've set to 0 at the start of the algorithm. J is 0. And so d will be found to be this divided by 2. A naught for me is 0. B naught is 1. So we have 1 plus 0 divided by 2, which is simply 1 upon 2 floor. And if you floor 1 upon 2, then we know that this is 0. So in the first sum, there are no multiples of 2. Then we set Sj. Sj is S of 0 equals Aj plus Bj, which is 1 plus 0 plus there was no carry, which is 0, minus 2 times the d that we found, which is 0, and we get S naught to be 1. And finally we set C to be equals to d, so C is set to be 0. So notice that again in the same way that we were adding over here, oops, in the same way that we were adding over here, we got C naught. There was no carry in the first one and the rightmost digit was 1. The same case is over here, that the rightmost digit is 1 and there is no carry. So if you follow this algorithm, you will get the same addition that you were doing this way, explained like this and explained in terms of this. Okay. How are we going to return the Sn minus 1 form? Well, once you have the digits, you can just write them down. You can just print them, right? So if you have all these numbers, you can just print the last number will be S naught, the next number will be this, and so on. You just print that number. So if you have 1, let's suppose the result in this case would be, the sum would be, so this would be my S naught, this will be S1, this will be S2, S3 and S4. So you have all of these digits and you just print them out. So the algorithm will just print out when it wants to print S4, S3, S2, S1 and S0, it will just print out 1, 1, 0, 0, 1. That's it. That can be in any form that you want. It can be in a string form, or it can be in a character form. That doesn't matter. That's up to you. That's up to the algorithm how it returns it. Okay. All right. We spent more time on this than I expected, but I guess it's worth it. Okay. So next thing is the multiplication of integers in binary form, and the way to do that is quite simple. Let's suppose if you want to multiply, the procedure is as follows. If you want to multiply 1 1 1 0 with 1 0 1, this is not 110, this is not 101, this is a number in binary digits. If you want to check the decimal, you will have to expand it. But the way to multiply this is as follows. Now notice when you multiply it with all digits. So you multiply the first digit with these, and you multiply the 0 digit with these, and you multiply the 1 digit with these, and then you shift it, right? But notice that your multiplication is always going to be with either 1 or 0. So your result is either going to be 1 1 0 or it's going to be 0 0 0, because if you're multiplying this string, this 1110, with this 1, you get the same thing, but if you multiply it with 0, you get 0, 0, 0. So these are the only two possibilities that you can get. So let's try this out. The first result will be 0, 1, 1. Then you shift, you place this over here, you multiply 0 with 110, so you get 0, 0, 0. You add 2 shifts in the next stage and you get again 1, 1, 1, 0. So 1, 1, 0. So you either get 1, 1, 0, you shift 1, 1, 0, or you shift 0, 0, 0. Okay. And then at the end you can just add these up. So this is addition 0, this is 1, this is 1, this is 1, and this is 1. And so that's the result of the multiplication of 110 and 101. Okay. Yes. Sumaya, Sn equals to C is outside the loop, definitely. Why are we subtracting from 2 times d? We are subtracting from 2 times d because notice that at every stage your a naught plus b naught is equals to 2 times c naught plus s naught. So to find s naught, you will have to do a naught plus b naught minus 2 times c naught. Similarly, for s1, you will have to do a1 plus b1 plus c naught minus 2 times c1. The d that you have is actually a stand-in for your current carry. So if you want to find s, you have to minus 2 times the current carry. So for sj, you will subtract 2 times the current carry, and then you will set the carry to be equals to d in this step. So you will, to find sj, you will subtract the 2 times the current carry, and then you will just set the current carry to be d. And this is of outside the loop, Sn equals to c. Okay. Why have we kept addition ka sign in multiplication? Is it supposed to be? We've done that because I'm an idiot. There you go. All right. Okay, and so let's just describe this procedure in terms of digits. So what we're doing is, let's suppose we have a times b. If we want to multiply the numbers a times b, you simply take the number a and let's expand b in terms of its digits. So let's suppose the digits of b were b n minus 1, b n minus 2, up until b naught. And so b can be expanded as b naught times 2 to the power 0 plus b1 times 2 to the power 1 plus b2 times 2 to the power 2 dot 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 bn minus 1 times 2 to the power n minus 1. Okay. So the reason I have not expanded a is that if this is my a, I don't need to expand it. I can write it as it is, or I can write 0, 0, 0 depending on what my digit is. Okay. And so we can write this now as simply, we can expand this by writing a times b is equals to a times b naught 2 to the power 0 plus a times b1 2 to the power 1 plus dot 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 a times bn minus 1 2n minus 1. And note the following. Here's something important, that if bj is equals to 0, then what you will do is you will simply put zeros there. This will simply be zeros. That row will not have anything to add to. But if bj equals to 1, then you will write a, you will write as it is, a as it is, but you will shift it A shifted j units to the left. So when you shift, so for example in the first one this was b0, this was b1, this was b2. When you were multiplying a with b0, you will shift it j units to the left. So bj was 1. There are going to be no shifts because j is 0 right now. So you just write it as it is. In the next case b1 was 0. You just write zeros as it is. Then in the next step you had 1, but now bj, so j is equals to 2, so you shift it twice because j was equals to 2 here, j was equals to 1 here, and j was equals to 0 here. Okay, so this multiplication is being done with first with b0, then with b1, then with b2, and it's every stage it's being shifted. And then lastly, once you have all the shifts, so after you have all the shifts, you just add the individual products. So once you have computed all of these numbers, you just add them up and that's your result. And addition is something that we've already covered. Okay. What if the last three rows had 1, 1, 0? I will answer this question at the end of the class if you don't mind, Daniel. Remind me at the end of the class and I'll answer it. Okay. So this is how you do multiplication, and if that's clear, let's just define the algorithm for multiplication. So the algorithm for multiplication is as follows. So first we start off, we say for, okay, let's define the procedure first. So procedure, the procedure is to multiply AB, multiply A and B, where A is of course equals to an minus 1 dot 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 a0, and b is equals to bn minus 1 dot 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 b0. Okay, and so we start the procedure by for j equals to 0 to n minus 1. If bj is equals to 1, then Cj is equals to A shifted j places, else, so else means Bj is not 1, which means it's 0, then Cj is simply 0. So Cj is the individual product that is being defined for each digit. And then finally what you can do, so we set p to be equals to 0, that's your final product. And so what we'll do is for j 0 to 1, 0 to n minus 1, now we are done with the multiplications, individual multiplications. So all we need to do is we need to add. So we will add p is equals to add p and Cj. So at the first step what you will do, this loop is doing nothing but adding all of the individual Cj's, and we've set that initially this was p was 0. So first when j is 0, on the first step you will be doing for j equals 0, you will be doing 0 plus c0. Then when j is equals to 1, since this is c0, what you will be doing is p is now, first p was 0, p is now c0, so you will do c0 plus c1. Then in the next step you will add this to c2, and so each of the individual Cj's keep getting added to p, and finally you get the product. And so the last step is then just to return this, return P, which is the P is the product A times B. Okay. So that's your algorithm. Okay, let me know if there are any questions here. Okay. So before we move on to the next section, there's just one more thing that we need to discuss, which is what's the complexity of these algorithms? So what's the complexity of addition and what's the complexity of multiplication? The thing to notice is that we're doing additions of individual bits in addition, and in multiplication what we're doing is we're simply doing some shifts and then we're doing some addition. So here's the first concern, which is the complexity of the addition algorithm. And so for complexity of addition, notice that we're doing at every step we are just adding bits. Now the question is, how many additions are you doing? So how many additions at each step? And that's simple to see. Notice that at the addition procedure, what you're doing is the following. Notice that this is one addition and another addition, but you don't need to do it again. Once you've done aj plus bj plus c, that's it. You don't need to do it in the next step. If you've done it, store it somewhere. And so if it's already in the memory, it's just two additions, and then you can think of this as a subtraction as well. So at each step, what you're doing is if we count subtraction also as an addition, then we're doing basically at most 3 additions at each step for a total of n steps, and therefore something roughly you're doing about 3 times n additions if you include that subtraction as well. And so the complexity of that algorithm is simply linear, O(n). Does that make sense? Not right now, Jafar. I could do that perhaps some other time, or you can check out in your book. Try going through the algorithm on your own. Follow these steps as it is and implement it. Okay, any questions for complexity of addition? Okay, and here is the complexity of multiplication. So in multiplication, you are doing two things. You are doing addition. So firstly, for multiplication can be broken down into 2 steps. You are doing some shifts and you are doing addition. Now addition, we've already figured out that it's going to be linear. If you are adding n minus 1 digits, then this is already, we know that this is going to be of complexity O(n). How many shifts you are doing? Well, the number of shifts are going to be at max. You are going to do one shift for every n. So these are n minus 1 shifts. So we have n minus 1 shifts. So if this is also linear, this is linear, and addition is also linear, therefore multiplication is also going to be a linear process. Okay. So both addition and the multiplication algorithm are linear in nature. Okay. So this is all I'm going to do for section 4.2. What you have is Now we'll move to section 4.3. There's a couple of things that I have not included from section 4.2. You can read that, which is basically the algorithm for div and mod. This is not officially included in the course. I'm leaving them out. And the next thing is modular exponentiation. So if you want to do that, you can do that. If you have any queries, let me know. But they're not officially included in the course. Okay. So let's move on to the next section, which is primes and greatest common divisors. So 4.3, we have primes and the GCD. Okay, question. Sir, can it be big theta instead of big O? Definitely, if you can put a lower bound, because I was talking about the upper bounds. The reasons I said it's big O is because I was putting an upper bound on this. If you can show that even the lower bound is also linear, then you can show that it is indeed not big O, but it's just big theta of n. Okay. Okay, I seem to have made a mistake here. Here is one mistake that I've done. Addition is ON, but actually what we're doing is we are doing n minus 1 additions. So the idea is that we are doing n minus 1 additions. So it's not going to be linear because n minus 1, we know that addition itself is linear when we multiply n minus 1 with, so this is going to be roughly equals to n minus 1 times 3n, which gives us a complexity. This is a linear term, ON, plus this is going to be something like 3n squared minus 3. So this term is not linear anymore, this is quadratic. And so overall it's going to be ON squared rather than ON. So that was a mistake on my end. Let me just check your questions. Sumaya, sir, but addition is inside the loop, so won't we consider that? Yes, that was my mistake that I made. Sir, multiplication में कहीं पे multiply नहीं हो रहा. Yes. That's true. Yep, multiplication basically boils down to shifting and adding. If you think about it, multiplication is simply a shortened version of addition. Any other questions? No? Should I go on? Okay, let's move on. Okay, let's first start with the definition of a prime number. I hope everyone here knows what a prime number is. So we start off by defining a prime. And a prime number is a number, an integer greater than 1, that is, that only has 1 and itself as its factors. So P is a prime if and only if the factors of P are 1 and P only. Okay, that's the definition of a prime number. So the first few primes are, we need an integer greater than 1. 1 is not a prime. So 2, 3, 5, 7, 11, 13, 17, 19, and so on are prime numbers, because every number is only divisible by itself. Okay. The next thing that we have is the fundamental theorem. So we are going deep into number theory now. So let's look at fundamental theorem of arithmetic. So the fundamental theorem of arithmetic is as follows. It says a very simple thing, and it says that every integer greater than 1, every integer greater than 1 can be written uniquely as a prime or as the product of two or more primes. So every integer, if you have any integer that belongs to, let's suppose that this integer x belongs to integers, then x can be written, so then either x is prime, so we have two possibilities. The first possibility is that x is prime, or the second possibility is that x can be written as p1 to some power, let's call it a1, p2, a2, p3, a3, dot, 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 up to pn, an. So you can write it as a product of primes. And the reason why I've put powers here is, for example, let's look at some number 6. So 6 can be written simply as 2 times 3. Let's look at 9. 9 can be written as 3 times 3. This is a product of primes, and actually it's 3 to the 2. If you look at 12, 12 can be written as 4 times 3, which is basically 2 times 2 times 3, which is 2 to the 2 times 3 to the 1. So, or if you just have a prime 13, then it's simply prime. So it's either a prime or a product of primes. Okay. Every number is fundamental theorem of arithmetic. Sorry about my handwriting. Okay. So that's something very simple to understand. Okay. All right. Question: how do we check? Question is, how do we check whether the integer n is a prime. Now, of course, the brute force method, the first thing to notice is that just check all numbers lower than n. So check from 1 to dot dot n minus 1 and see if any of them divide n. If they divide n, then you have a prime. Then you don't have a prime, but if you can't find anything in these, then if you can't find a divisor from 1 to n minus 1, then of course that would mean if you find no divisors, then n is a prime. That's the first thing we can think about, right? But of course we don't need to do that. The next thing to notice is we don't need to check all the numbers, we need to just check all primes, because the fundamental theorem of arithmetic tells us that each number is either a prime or is divisible by some primes. So if we just check all the primes less than n, then we can check whether n is a prime or not. And the last thing to notice is that we don't even need to check all these numbers less than n. We only need to check primes less than square root of n. Okay. So the idea is, if you want to check whether 27 is a prime, all you need to check is primes less than square root of 27. Now the square root of 27 is going to be somewhere between 5 point something. So all we need to check is primes less than less than n equals to 5. So it was actually primes less than square root 27, which means we can just check all the primes less than 5. The primes less than 5 are 2, 3, 5. If we divide it by 2, it's not divisible, but if we divide by 3, it is divisible, so 27 is not a prime. Similarly, if you want to check 101 is a prime or not, all you need to do is check primes less than the square root of 101, and the square root of 101 is definitely going to be 10 point something, because the square of 10 is 100, and so we need to check all primes less than 10. Now we can check, let's suppose, is it divisible by 2? No. Is it divisible by 3? No. Is it divisible by 5? Doesn't look like it. Is it divisible by 7? Also doesn't look like it. And so 101 is a prime. So all you need to do is check less than 10. Okay. That's one way of checking whether a number is prime or not. So all you need to do, I will leave this up to you why we have this nice little condition. I want you to think about why is it that we only need to check numbers less than square root of n. Why don't we need to check the rest of the numbers? Why didn't we check 11, 12? Maybe this number would have been divisible by 11. Why didn't we check that? So questions. Why only check primes less than square root of n? And I want you to think about it. I won't answer that question right now. Okay, so let's look at another problem. The next problem is question: how to find all primes less than x. Let's suppose x is some integer, right? How do I find, let's suppose x was equals to 30. How do I find all the primes less than 30? Now the first approach is, of course, check every number. The first simple brute force approach, the brute force approach is check whether the numbers, let's suppose from 1 to 30 are prime. That's the first thing to do, and that's a very time consuming thing to do, because checking whether a number is prime or not, for each number you will need to check whether it's divisible by the primes less than square root of n. So if I need to check 26, I will need to check whether it's divisible by all the primes less than or equals to square root of 26, and I need to repeat this for 1 to up until 30, right? That's the first approach, and this is a very slow approach. The next nice thing, also referred to, the method referred to as the sieve of Eratosthenes, is as follows. Let's list down all the numbers from 1 to x. So the first step is list down all numbers from 1 to x. So let's suppose I write them down: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, and 21, 22, 23, 24, 25, 26, 27, 28, 29, and 30. The next thing to do is remove all multiples of the primes less than square root of x. So here's the procedure. The square root of 30 is going to be again somewhere between 5 point this. So I need to remove all multiples of what are the primes less than 5 point something. There are 2, 3, and 5. So I start off from 2, I leave 2 as it is, and I remove the multiples of 2. So 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. These numbers I am sure are not going to be primes, and I've removed them from the list. The next thing to do is to remove multiples of 3. So removing multiples of 3, leave 3 as it is, but multiples of 3, 6 is already removed. We remove 9, 12 is already removed, 15, 18, 21, 24, 27, and 30. And finally we remove let's remove the multiples of 5. So leave 5, 5 is a prime, and we have 15 is already removed, 20 is removed, 25 is removed, and 30 is removed. And so all the remaining numbers, so let's look at these. 1 is of course not a prime. So 2, 3, 5, 7, 11, 13, 17, 19, 23, and 29. I am guaranteed that these numbers are going to be prime. And that's a much easier way of doing that, instead checking whether 2 was a prime, 3 was a prime, 4 was a prime, and so on and so forth. How is this faster than the brute force algorithm? Kepler, try doing it for 100 and you will realize it. What if the number was far greater than 30? It would be time consuming itself. Well, so the idea is, let's check the number of operations. What you're doing is, let's suppose we have 3 primes, and all we're doing is we're removing multiples of 3, and it will take about 30 steps per prime, and so it will only take about 3 times 30, that is 90 operations to do. Now the question is, can you check all of these numbers are prime in less than 90 operations? And the answer is, I want you to think about that answer. It's actually going to be much larger than 30. And if it's not clear, think about, let's go from 1 to 100 rather. Let's suppose you have, your list is from 1 to 100. The primes less than 100 are, we need to check primes only less than square root of 100. So that means if 100 numbers need to be checked, all you need to do is remove the multiples of, so this is less than 10, then the primes less than 10 are 2, 3, 5, 7. So you will just remove the multiples of 2, so you will have then multiples of 3, multiples of 5, multiples of 7, so you have 100 times 4, which is again 400 steps to do. And this is going to be again less than, I guarantee you that this will be less than just checking whether each number is prime or not. And okay, here is an exercise. Write an algorithm to check whether n is a prime, and the next thing is, what is the complexity of this algorithm? What is the complexity of this? And so whatever the complexity of this algorithm is, you will remember that you will need to run now to check. For example, if you want to check for how many primes less than x, you will have to run less than or equals to x, you will have to run this algorithm, whatever algorithm you've written, you have to run algorithm x number of times. So whatever the complexity of this algorithm is, let's suppose you wrote an algorithm that was O(n) squared, then you will need to run it x times O(n) squared, which means its complexity is going to be O times x times n squared. So it could be cubic, it could be something, but I invite you to write this algorithm and check for yourself that it's going to be much slower. No, because it's 100 perfect square while root 30 was 5 something. Okay, I missed the conversation. What if the number was far greater than 30? It would be time consuming itself. That's already answered. What if x is equals to 1000? Will 10 not be included? Because you included 5 in the previous example. No, because it's 100 while root 3 was. Okay, yeah. That's it. Of course, we already know if it's 1000 is equals to (10 cubed), then we already know that this is not a prime. So you can even just remove it from your list. Okay. And so the idea is, when you want to check less than 1000, you will need to do square root of 1000, which is going to be what? It's going to be 10 root 10. So you just multiply them and figure out what the number is, and you will then check all primes less than 10 root 10. Okay. Yeah. So you will check all those numbers. Okay, let's move on. That's how you check for primes less than a certain number. We have a nice little theorem now which tells us how many primes there are in the whole real line, and the answer is there are infinitely many primes. Okay, and so let's prove this, and the proof is actually quite elegant. There are infinitely many primes, and we will prove it by proof by contradiction. Suppose there are finitely many primes. Well, if there are finitely many primes, then let's suppose these primes are from P1. So let's suppose these primes are P1, P2, and since they're finite, let's say there are n of them. I don't know, n could be a large number, but let's suppose there are n primes. And so consider the number q, which is found by multiplying P1 with P2 with P3. We are multiplying them, this is a multiplication, up until Pn, and add 1 to this. Okay. And so now here's the idea. So by the fundamental theorem of arithmetic, we have two possibilities. The possibility one is that q is a prime, and the possibility two is q is a product of primes. Okay, and so the first possibility, if the first possibility is true, then we already have a contradiction, because we assumed that we have listed all of these primes P1 to Pn, and if P is itself a prime, then you have a contradiction because you found another prime, So that's a contradiction in the first possibility. In the second possibility, we're assuming that q is a product of primes. So what are these primes that are dividing q? So let's suppose q is a product of q1 up until qm. Let's suppose there are some primes that divide q. Now the question is, are they included in this list, P1, P2? So q has a prime divisor, but notice that if q has a divisor that is prime, then q, which is being written as P1 up until Pn plus 1, if I consider some pj from this list, let's suppose I take one prime from this list. Okay, and so the question is, does pj divide q? And the reason I'm taking from this list is because I can't make other prime numbers. These prime numbers can't be from anywhere else, they have to be from this list, because my assumption was that I have listed down all the possible primes. And so I have to take some prime from this list and show that does it divide q or not. And so if it divides it, so let's suppose I can rewrite this equation as q minus p1 dot 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 pn. And so if pj divides q, then notice that pj should also be able to divide q minus p1 to pn, because if it's a divisor of q, then it's going to divide this number, and if it's a divisor of, it's already in this list, so it has to divide this. So pj should be able to divide q minus p1 to pn, but that's asserting that pj should divide 1, because q minus this is simply 1, which is a contradiction. So in the first possibility, when we considered P is a prime, we found a contradiction because we found another prime. And if Q is a product of primes, then these primes must come from this list. But we've shown that none of these Pj's would be able to divide this Q minus P1 Pn, because if it did divide Q, if it was a divisor of Q, then it should have been able to divide this subtraction, because for example, if you have a number, let's suppose if you have 3 divides 9 and 3 divides 6, then it's able to divide 9 minus 6 as well, because you can take 3 common from it. 3 times 2, sorry, 3 times 2, 3 times, if you have if you have 9 minus 6, I can take 3 common from here, which is 3 minus 2, and 3 times 3 minus 2 is 1. The result is a multiple of 3, and you can divide it by 3 to get 1. So if our assumption is that Pj divides Q, then you should be able to take Pj common from here and common from here as well. But the result of this entire thing is just 1, and Pj, a prime number, can't divide 1. So that's a contradiction. Okay, is that clear? And so the contradiction is that there are finitely many primes, and so the result is we prove, therefore the result is that there are infinitely many prime numbers. Okay. Jafar, sir, ये algorithm आप करवाएंगे? No, I won't do this algorithm. This was just as a mental exercise for you. You can try it out on your own. Just take out any coding language and write down a code to check whether a number is prime or not. Okay, that should be easy to do, and I recommend that you do it. Okay, next thing we have a theorem, which is the prime number theorem. And the prime number theorem answers a question, and the question is, how are primes distributed along the number line? So if I draw a number line, how many numbers do I need to traverse before I encounter the next prime? Okay, and that is actually an open problem, but something that we can say about this distribution is that if the ratio so let pi x be the number of primes less than and equal to x. So let's suppose you've gone as far as x in the integers. You started from 0 and you've gone up until x. So if you're looking at how many primes would you encounter in this list, so that's pi of x. And the idea is that the ratio of pi of x divided by x over ln x approaches 1 as x grows without bound, which in other words it's saying that the limit of x approaches infinity of pi of x over ln x is equals to 1. So essentially what we are saying is that pi of x is approximately equal to x over ln x. So if you want to know how many how many primes less than 10, the answer is the primes are going to be less than 10 upon ln 10, approximately equal to this number. Okay. All right. So there are some, not all the things about prime numbers are known. There are lots of open problems for prime numbers. And the problem is that we don't really have a list of all the infinitely many prime numbers. If you consider odd numbers, let's suppose, let me write that in. So if you consider odd numbers, you know that even though I don't have a page somewhere that lists all of the numbers, I know that I can simply write it as 2n plus 1, and this is a formula that tells me all the odd numbers. If I want to list all the even numbers, well, I just have 2 times n, where of course n is an integer for both these cases. But the problem is there is no such formula for listing primes. That's the first problem. And secondly, there are some open problems as well. So there is a conjecture called the Goldbach Conjecture, which says the following. And the Goldbach Conjecture says that every even integer n where n is greater than 2 can be written as a sum of 2 primes. So the idea is if n is equals to 10, you can write this as 3 plus 7, and it's the sum of 2 prime numbers. If you have n equals to 12, so if n is equals to 12, you can write this as 5 plus 7, of course. And so every even integer can be written as a sum of 2. So if you have 22, you can write this as perhaps 17 plus 5, and so on. Now it's called a conjecture, it's not called a theorem, because no one has proved this yet. No one has proved it, but it has been verified for lots of even integers. And so if you want to become a famous mathematician, just try and prove this. It's a very simple conjecture, but no one has been able to prove it yet. And the next thing that you have is also a conjecture called the twin prime conjecture. And the twin prime conjecture says that there are infinitely many pairs of prime such that p and p plus 2 are both prime. That is, they're just separated by 2. So for example, if we have a list, for example, let's suppose we know that 3 and 5 are prime, and their difference is just 2. We also know that 11 and 13 are prime. And if you notice, these numbers get more and more separated, but every now and then you do encounter 2 primes that are just separated by 2 numbers. So if we check the list that we made for less than 30, so these are separated by 2. Now 7 and 11 are separated by 4 digits, but 11 and 13 have just a gap of 2. So these are twin primes, but there is now a gap between 23 and 29. But of course, if you notice that 31 is a prime, so 29 and 31 are also prime. And so the idea is, the conjecture says that there's infinitely many twin primes. And people have been getting closer and closer. These bounds have been reduced to less than even, I think, about 26 now, or I don't know, I'm not sure. Or maybe 2 point something. Lots of progress has been made, but the idea is we still don't have a proof for this, so it's not a theorem yet. Okay. Sir, can we stop now? We've almost done. I still want to just mention a couple of things because I actually wanted to move to the next section, but let's not do that. Let me just mention 2 different things and then we'll stop. Okay. So these 2 things are something that you already know. The first thing is the GCD, which is the greatest common divisor, and the LCM, which is the least common multiple. And I'm sure you know the definition of these things. All I want you to know are these 2 new things. The first thing is, if so we define relatively prime, and the idea is that if GCD, if the greatest common divisor of A and B is equals to 1, that is, they don't have a common divisor other than 1, then A, B are called relatively prime. Okay. There are, of course, simple techniques to finding the GCD of 2 numbers and the LCM of 2 numbers. The GCD of A and B can be found by, so if A is P1, if A is P1 A1, P2 A2 dot 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 P n an, so A is being written as a product of primes, and if B is P1 B1, P2 P2 dot 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 Pn Bn, again B has been broken down into a product of primes, then GCD is simply P1, the minimum of the exponent on P1 for both of these, so minimum of A1 B1, P2 minimum of A2 P2 dot 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 Pn minimum of An Pn. And I will just do this last thing where I just explain this as an example. So for example, if you wanted to find the GCD of 27 and 12, then 27 can be written as 3 cubed and 12 can be written as 2 squared times 3, 1. And so then the GCD of 27 and 12 is, so the first prime in this list is 2, and over here notice that 2 has power 0, so the minimum of 0 and 2 is simply 0, so 2 to the power 0. Let me just write this as minimum of 0 and 2 times 3 times the minimum of the power of 3 is 3 and the power of 3 over here is 1, and so the result is 2 to the power 0 times 3 to the power 1, and so the GCD of 27 and 12 is 3, which you can verify that the greatest common divisor is 3. There is no number bigger than 3 that can divide both 27 and 12. Okay. And for the GCD, you take the minimum for the LCM, it's actually quite similar. You take the maximum of these powers. So I know I'll stop, but this is, I promise this is the last thing. LCM is simply, LCM of AB is simply B1 max A1 B1 dot 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 Bn max An Bn. And that's it for now. Okay, any questions? Danya, you had a question that I said I will answer at the end of the class. Any more questions? Tanya, could you repeat the question that you had? I think it was from the addition of primes, addition of integers. Online में I actually don't think that's true, because I'm much slower in writing these things as I was in writing them on the board. I don't think that's true. Okay, maybe you're right. Okay. Okay, I believe you. Maybe I am. I'll try to cut down a bit. Anything else? So the question is, that if I had 1 and 1 and 1 plus like this, the question is how do we carry, right? That's the question. For this one, what we do is we know that the result is going to be 3, and remember that we wrote it in terms of how many multiples of 2 do you have, so 2 times c plus the remainder, and 3 can be written as 2 times 1 plus 1. So the carry digit is 1 and the last digit is 1, so we write 1 over here and you carry 1 over here. Does that make sense? In multiplication, that's the same procedure you do if you have something like, if you were multiplying two numbers if you were multiplying two numbers, let's say you had some number here and some number here, you're multiplying them, and so put a cross here, put another cross here, and let's suppose put some number here, 1 0 1 1 1, and then 1 1 1, and then 1 1 1. Now let's do this addition. This is simply 1, this is 2, so this is 2 can be written as 1 times 2 plus 0, so the last digit is 0, or you can just think of 2 as 1 0, put the last digit here and you carry it over here. Now this is 4. Now the carry over here is, of course, now this is 4 is equals to 2 times 2 plus 0. What you can do is you can think about this as writing the last digit still remains 0, but the idea is you have to carry 2 now. So if you carry 2, this is again 4, 0, carry another 2, this is 3, this becomes 3 is simply 2 times 1 plus 1, so this is 1, and then you have another carry of 1 here, which becomes 1, and so the sum of 1 1 1 1, this becomes this, and so this is actually the multiplication of 1 1 1 with 1 1 1. So you had this number once, then shifted once, then shifted twice, add them all together, and this is the sum. Does that make sense? Okay. Cool. Is that it? Any other questions? Okay, Jafar, I will ask your TA today for the assignment grades, and I will let you know how far the checking is done. Okay, I will just send him an email today. Anything else? Okay, bye-bye. Thank you.